unit rate is a comparison of two quantities where the second quantity is 1 unit. Now a unit can be anything, right? We could be talking about miles, we could be talking about inches, seconds, minutes, hours, whatever our units are for that specific problem. The second quantity has to be 1. What does that look like? Well, let's take a look. Something that you may, a unit rate that you're probably most familiar with. 30 miles per hour. Right? Whenever you're driving in a car, you're going a certain speed, and that speed is represented by a unit rate. 30 miles per hour. Where our ratio is 30 miles to 1 hour. The second quantity in this unit rate is hours. And we know that this is a unit rate because we are using 1 single hour. That's what it means when it says where the second quantity is 1 unit. Now, if I said I was driving 60 miles every 2 hours, would that be a unit rate, you think? No, because I'm using 2 hours. My second quantity in that case would not be 1. Another example that you might be familiar with, if you are into music, 120 beats per minute. Anyone ever heard of that before? Beats per minute, BPM? Fellow people? Good. So our ratio here is 120 beats, right? Beats is a unit. Every 1 minute. That 1 minute being our second quantity. And we know that it's a unit rate because our second quantity is 1. If I said, oh, this song that I'm listening to is 60 beats per 30 seconds, that would not be a unit rate. It's still a rate, right? A rate is just a comparison of two quantities, and by quantities we mean numbers. But the second quantity has to be 1. Miles per hour, beats per minute. If you're talking about rainfall, it's typically in inches per hour. So this is basically what a unit rate is. Let's write a quick non-example so we know what a unit rate does not look like. Like I said, 60 miles every 2 hours. Like I said, 60 miles every 2 hours, that's still considered a rate. But because our second quantity is not 2, because our second quantity is 2 instead of 1, we can't consider it a unit rate. And in this circumstance, unit rate is just a fancy term for slope. The reason why we call it something different is because, as we've been seeing with our slope finding, right, it's just a line on a graph. It doesn't mean anything, it doesn't have any context, it doesn't have any real world application necessarily. But what we're going to be talking about today is finding slope within a certain real world context. Miles per hour. This is a real world context when you're driving. Beats per minute. Again, it's a representative of slope in a way that applies to certain songs. Every song has a certain beats per minute. That's a unit rate right there. So once you get that copy down, you can glue in your Misty Mountain Storm square that I passed out. It's going to be our first example that we talk about. Move this down a bit. Give you guys like a minute to get that glued in and finish writing. The volleyball game? We have a faculty meeting today. Is it at home?
Yeah.
What time does it start? Okay. Should I go, Darius?
You need to watch some sports.
Oh, okay. Don't you guys switch? Like 8th grade goes first later or something like that?
I think that's
Next week? Okay. I'll try my best. We'll see. I don't know how long the faculty meeting is going to go. At the moment, maybe. I'll definitely go when the 8th graders go first. Because I don't know many 7th graders. I only know the 7th graders from summer. You playing like rudder, right? Okay. Shouldn't be too bad. All right, let's go ahead and get this example written down. I apologize in advance. Today is going to be a little bit more word writing than we're used to. Because these are kind of, I don't want to say they're word problems, but you need words to understand the context. The math is exactly the same as what we've been doing, right?
Yeah.
We've got a proportional relationship. All we need to do is count the rise and put it over the run. Nothing about the process is different. It's just understanding our answer is going to be a little bit different because we need units. So this graph here shows a constant rate of change. You're going to hear that phrase a lot over the next 4 years. Constant rate of change for snowfall on Misty Mountain. And I'm going to abbreviate the word mountain with MTN because I ran out of space.
What?
It says this graph shows a constant rate of change for snowfall on Misty Mountain.
Oh, I thought it said MTA.
Oh, sorry, yeah, MTN. Like Mountain Dew. Don't they abbreviate it with MTN?
Yeah.
Yeah, that's okay. That's what I thought.
Yeah.
Mountain's too long of a word. So MTN means mountain. Plus, you see on the top it says Misty Mountain. So MTN, that's what that means. All we have to do here is find the unit rate of snowfall every hour. So anytime we're finding a rate, we have two different units. Miles per hour, beats per minute. In this case, we have inches per hour. Our snowfall is measured in inches, kind of like I mentioned with rain earlier. And our time is going to be represented by hours. So if we want to, we could fill in the spaces here on this graph. Each notch on this graph, how many hours is each notch here? What would this first notch be?
5.
Well, 5 is right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What about our snowfall in inches? What's my first notch here going to be?
1.
1 again. Good. 1, 2, 3, 4, 5 in the middle. 6, 7, 8, 9, 10 up on the top. This is just going to help us figure out what our points are. Why is it so loud?
Whoa.
It's a little music. All right, let's go ahead and find us some points here. Does anyone see a nice point on this line that crosses our coordinate evenly?
1 and
2 and 4. So 2, 4. Yep, that looks good. There's a couple of them.
4 and 4 and 7.
4. I think 4, 6 would be right here.
Or 8.
4, 8. There we go. That looks better. So this one here is at 2, 4. This one up here is at 4, 8. Let's stick with those two. Those look great. Now, we've got a graph. So what can we do here to find our slope? What's the process called? Something over something. Rise over run. Exactly. So if we start at 2, 4, and we're rising up to 4, 8, we're going to go up 1, 2, 3, 4 spaces, just like that. We went 4 units up. Number M is equal to rise over run. So we found that our rise here is 4. How many units do we have to run over now? 2. 2 units to the right gives us a run of 2. Now, we know how to find slope, right? Should be second nature by now. But there's a reason why we have a context for this problem. What does this 4 here represent? What would the units be on my 4?
What?
4 inches of snowfall per hour.
Exactly. See, look, we're going 4 on the y-axis. My y-axis, the units are in inches. So my rise would be 4 inches of snow. We could just say inches. And what does my x represent?
Out.
Time in hours. So 4 inches of snowfall every 2 hours. Now, would that be a unit rate? No. Why not? Because it's not a 1 on the bottom. So we got to simplify this to a point where we're looking at how many inches of snow falls in 1 single hour. All we got to do for that is simplify.
2.
4 over 2 becomes 2, good, over 1. So now we see that on Misty Mountain there is 2 inches of snowfall every 1 hour. Therefore, M is equal to 2 inches of snow Morning, Jack. Thank you. 2 inches of snow every 1 hour. Go ahead and write that out. It's our answer explained within the context of this problem. So we're used to just saying, oh, M is equal to 2. But now we have to say that M is equal to 2 inches per hour. So we're going to rewrite this just to clean it up. 2IN/HR. And that's going to be our answer. Was there anything different about the way that we found this slope? Did our rise over run process change at all?
Yeah.
No.
Oh.
We still went from left to right. We rose up 4, ran over 2. We drew our little slope triangle. Everything is the same. The only difference is we have to pay attention to what our units are and include the units in our answer. That's the only new thing we're adding today, is these units. So because our slope is always change in y over change in x, your units will always be the units of your y-axis over the units of your x-axis. Inches per hour. And this right here is our unit rate. So, in the interest of time, we're going to go ahead and get started on 15.5 together, because I'm not going to spend time adding in a whole nother example with a table in our notes. Number 1 on this worksheet is a table, so we'll go through that together, and then we'll go ahead and get to work. Sure.
Wow, where is it?
Don't put it away. So 15.5, let's take a look at number 1. We're talking about a geese or goose. Geeses, whatever you want to call them. Canadian geese. This thing is like a brand of jacket or something, isn't it? Canadian goose? I don't know. Canadian goose? I feel like that's a brand of jacket. Maybe I'm tripping. Or maybe that's what they make jackets with, is Canadian geese? I don't know. Something like that. So, number 1, a Canadian goose migrated at a steady rate of 3 miles every 4 minutes. 3 miles per 4 minutes. Is that a unit rate? No. Why is that not a unit rate? Because it's not 1. Exactly. 4 minutes. This means that this is not a unit rate. We got to figure out what the unit rate of this relationship is. For that, we can fill out a table. Our x is going to be our x is going to be representative of time, and our y will be distance in miles. Time, of course, being in minutes. So right off the bat, we know that our final answer is going to be in miles per minute. Okay? We've got some values on this table, 4, and then 8, and then something, and then something, and then 20. And then on the y, we've got something, and then 9, 12, and something. So let's try and see if we can figure this out. If these geese fly at a rate of 3 miles every 4 minutes, and we've got 4 minutes on this table, what's the distance that's going to correspond to that?
3.
3, right? It says right there in the question. They go at 3 miles every 4 minutes. So after 4 minutes, they've flown 3 miles. Give me a thumbs up if you see what I'm talking about there. Okay, I appreciate that. Let's fill in these blanks up on the top. How do we get from 4 to 8 plus 4? So if we're going at a steady rate, this next box is also going to be plus 4, which is 12. Good. This next box will be plus 4, which gives us 16. And that lines up nice and perfect with our 20. That's also plus 4. We can figure out our change in y on the bottom as well. How do we get from 9 to 12? Plus 3. So what's going to come right after 12? 15. But what would come before 9? 6. Good. It's a little kind of like a puzzle kind of to solve. If you've anyone ever played Sudoku before? A couple people. Super fun. I mean, well, if you like math, Sudoku's fun, but it's kind of like a little Sudoku puzzle. You're like, you got to figure out what goes where based on the slight information that you have. I used to be really into Sudoku, but I don't have time for all that now.
What?
Sudoku. It's a game. If you saw it, you'd probably recognize it. But anyway, that's not what we're talking about. So we see our change in y is plus 3. Our change in x is plus 4. We know that m is equal to the change in y over the change in x. What's my change in y here? 3. What's my units on that 3? Minutes? Miles, right? Take a look. My plus 3 is in miles. What's my change in x? 4. And what's my units on that? Minutes. So look at the slope we just found. 3 miles every 4 minutes. Does that sound familiar somehow? It's right there in the question. The geese fly at 3 miles every 4 minutes. We found 3 miles every 4 minutes. Can we simplify 3 over 4 at all? No. So here's what our unit rate is going to be. 3/4 of a mile every 1 minute. In our notes, we've got a nice even whole number that we simplify, but now we can't simplify 3 over 4. So we're going to write 3/4 of a mile every 1 minute. How many laps around the track out there would 3/4 of a mile be? How many laps is that? Well, how many laps would 1 mile be? 4 laps. So 3/4 of a mile would be 3 laps.
Oh, I was down 3.
3/4 of a mile is less than a mile, right? So if you're out there running the mile, right, you got 4 laps. Once you get finished with 3 laps, right, you just flew as far as these geese can fly in just 1 minute. Anyone ever run 3 laps in 1 minute? I don't think that's even humanly possible to do. When I was in school, I could do 3 laps in like 12 minutes probably, so that might be, relatable. But these geese are flying 3/4 of a mile every 1 minute. So if you get these geese out there on the track during PE, they're going to go 3 laps in 60 seconds. That's how fast these geese are flying.
They're like ostriches, like ostriches are fast.
Yes, ostriches can't fly, but they are very fast. Ostriches can run super fast, yeah. So that's what this means in the context of this problem, right? The point of all this is to put some meaning behind this math that we're learning. This is kind of going to be a part of every lesson moving forward. Once we learn the actual math, we're going to figure out what that means in the real world. So these geese are flying 3/4 of a mile every 1 minute. The last part of this is we could also graph this relationship. So on the bottom, we've got time in minutes. On the y-axis, we've got distance in miles. But let's be careful here. If this notch here is 10 minutes, what's the number going to be for this first notch? Kamani? 2. Great job. 2 minutes. Then we've got 4, 6, 8, 12, 14, 16, 18, 20. Squeeze them in there as much as you can. What about on the what about on the y-axis? What's my first notch going to be in miles? 2 again. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So if these geese are flying 3 miles every 4 minutes, we're going to go to 4 minutes on the x. We're going to go up to 3 miles on the y, which is right there in between 2 and 4. It's not going to be nice and perfect. You can't barely even see the coordinates anyway because of our copier, but try your best. 4 miles every 3 minutes. Let's fill out the rest of this table then. 6 miles, 6 miles every 8 minutes. We're going to go to 8 minutes on the x. Will count us up to 6 miles on the y. Make our point there. Just try your best. I know the graph is not very clear.
Colorful.
Well, yeah, but clear. You can't even see the grid. The next point we've got is 12, 9. So we'll go over 12, up 9, right in between 8 and 10. 16, 12. That one's a little bit easier for us to find. And 20, 15. So we should get 1, 2, 3, 4, 5 points that all make a nice straight line. You can use your rulers to connect those 5 points. Thank you.
Wait, did we get a new paper?
Yes, let me grab it for you in just a sec. Here you go.
Thank you.
And there's our line right there. Just to review for our quiz tomorrow, what type of relationship do we see here?
A diagonal.
Diagonal, that's the type of line, that's great. Linear, good. It's definitely a straight line. I'll give you a hint, it starts with a P. Proportional, that's right. So a proportional relationship, this will be on the quiz, so listen up. A proportional relationship has 2 qualities every single time. Just like we said over here, linear. It's got to be a straight line, right? What's the second condition? Anyone remember? Uh-oh. It's got to go through somewhere.
Origin.
There you go. It's got to go through the origin right there. That's a proportional relationship. All right.